Most organic chemistry courses follow a similar structure, which begins by presenting you with a set of tools and ends by asking you to use those tools to solve puzzles. Those tools are reactions, and the puzzles are synthesis problems. On this channel, we believe the best way to improve at answering any type of organic chemistry problem is through practice, and that's exactly what we do. In this video, I will share with you a series of synthesis problems that you may encounter in Orgo 1, give you an opportunity to practice, and walk you through exactly how I would approach each problem. Here we go. Let's try to synthesize the purple product from the starting material. Again, I encourage you to pause it and try to think about this on your own, and then I'll show you how I went about thinking about this problem. Some problems like this one can be thought about in a forward direction, but as the problems start getting more difficult, retrosynthetic analysis scales up much better. So it's probably a better idea to practice that now. I always begin these problems by asking what stayed the same and what has changed. Essentially, the entire carbon backbone stayed the same. They're the same number of carbons, are all in the same positions. However, the position of this double bond has moved. Now, if we were still doing one-step problems, you would have to ask yourself, how do I move a double bond? But because these are synthesis problems, they're likely to take more than one step. So you can ask yourself, how do I create a double bond? What comes to my mind when I think of ways to create a double bond is the elimination reaction of alkyl halides under the E2 mechanism. Remember, there's normally more than one good way to solve a synthesis problem. For example, in this case, other ways to create a double bond include acid catalyzed dehydration of an alcohol and alkyl halide elimination via the E1 pathway. Now, one of those pathways works for this example, the other one does not. I encourage you to try each on your own, and in the comments, ask or explain why one of them works and the other one does not. But back to the problem at hand, we now have this intermediate, and we need to end up, or at least, or come from this starting material. So we have to think, how do we get an alkyl halide from an alkene? We know we can do that with an addition reaction. However, we need something else. If we take this alkene and add HBr, we would end up with bromine being added to the more substituted carbon, which is not what the intermediate we need is. So we need to ask ourselves, how do we add bromine to this less substituted carbon? And we just add peroxides. So that's a terrible box, but bear with me. That is a complete synthesis for our first problem. This is a fun one. Synthesize this purple product from the black starting material. Pause it and give it a shot. So looking at things that stayed the same, I see the same carbons in the same positions. However, we lost this alcohol and formed carboxylic acid in a different position on a different carbon. So we can ask, how do we create a carboxylic acid? And this is where the variation appears. The first method that comes to mind is the oxidation of an alcohol with a strong oxidating agent like this. And to end up with this carboxylic acid, we would need this primary alcohol, which is an intermediate that is not the same as the starting material. So now when comparing the starting material to this intermediate, the only things that changed were the positions of this alcohol. So just like the first problem, instead of asking how do we move an OH group, it's better to ask how can we create an OH group. We know we can create an alcohol from an alkene. The only alkene we can create with this carbon backbone, it's kind of a bad sketchy drawing, I guess, is this alkene right here. Also, this alcohol is in the less substituted position, so we need to use the anti-Markovnikov hydroboration reaction to end up with alcohol in that position. Now we just need to create this alkene from this starting material, and that can be done with acid catalyzed dehydration. So this is slightly better box. This is one way of formulating this synthesis. Let's try another. But before we start, it's important to note that D, if you don't already know, is the symbol for deuterium, which is just an isotope of hydrogen. It reacts just like hydrogen, but it can be picked up differently on NMR, and it's used to identify or track the movement of hydrogens during a reaction. And you'll see it used a lot in synthesis problems to identify if you can have control over what you do with your hydrogens. So anytime you see a D as the end product of a synthesis, you have to assume that you're thinking in hydrogens. So the question you have to ask is, how do I add just one hydrogen and nothing else to a molecule? And that question goes hand in hand with the alternative question of what molecules can accept just one hydrogen. And the answer is you're thinking in acid-base problems. So if we're adding a hydrogen to something, that means that our intermediate must be basic. And a way that we can make sure that a carbon chain, or the intermediate for this case, is basic is by having to have an effective negative charge. When you are asked to create a negative charge on a carbon in an organic chemistry synthesis problem, you are more than likely working with a Grignard reagent. Now, I say this is essentially equal to this because of the charge on this carbon being equivalent to the charge on this carbon. And you can tell that by looking at the natural charges or the oxidation states of the bromine being a -1, magnesium being +2, and then considering the fact that the entire molecule is a net zero charge, that means that that carbon is a negatively charged carbon. It's an anion, and therefore is basic. So now we can fill in this first step with the reagents. We have a strong base. We have That base is weak conjugate acid. And now we ask, what can act as a slightly stronger acid than this, but would be a weaker base than than the conjugate base of this. Most of the time you just use water, but because you have this deuterium as the hydrogen replacement, we would use D2O. Now, continuing to think backwards, at this point, it should become pretty procedural because we just need to think about how you create a Grignard. And that will almost always be by running magnesium through a starting material that is an alkyl halide. Now for our last step, we can recall that our starting material is an alcohol. So we simply need to convert an alcohol into an alkyl halide. There are multiple ways you can do this, but I like using PBr3 because that's very controllable, but it can also be done using HBr, which would protonate the alcohol, and then you'd have a substitution reaction. But either way works. So our final synthesis problem solution would look like this. Here we go. Pause it and try this one, and then I will show you how I would think about it. Okay, if you're ready, this is how I would go about doing this problem. I would once again start by thinking about what changed between the starting material and the product. It should be pretty easy to see that there was a ring in the starting material that simply is not there in the product. So our next thought has to be, how can we just lose a ring? We could do that by thinking about what a ring is. For this problem, or for anytime you see cyclohexane, that is 6 carbons, at least, all having 2 bonds to other carbons. If we look at the product, we do still have 6 carbons with the 7th carbon that we drew in there. However, 2 of those carbons are missing the second bond to carbon. What does that mean? A carbon-carbon bond was broken. So when you're thinking about how you can break carbon-carbon bonds, especially when you see these carbonyl groups in your product, you can almost confirm that ozonolysis was involved. And ozonolysis requires the starting material or the intermediate from which the product is derived to have a carbon-carbon double bond. Now, this is what stumps a lot of students. Identifying where in this carbon chain or in this structure the double bond originated. If you're having trouble visualizing it, the method I would normally use to do this is by first identifying any abnormalities in the chain. In the product, you have that methyl group. In the starting material, you have that methyl group, right? Then I would draw prospective double bonds on all of the adjacent carbons. So in this case, it can be here, could be here, or it could be here. You might realize that the first two are the same, just like these two are equivalent. So we can really cross one of these out because you're getting the same thing. And having 3 when you could have 2 can get confusing unnecessarily. But my next step would be drawing the product if we were to cleave these double bonds. We would end up with these 2 products, the first of which looks much more like the product we're looking for. So we know that this intermediate is the alkene that we're using. Ozonolysis is written in 2 steps, and with ozonolysis, it is very important that we get our reagents right, because after the first step, being a constant O3, the second step can lead to different products. For this, because we have aldehydes, these being aldehydes, the second step is CH3 to S. Had we used the other common reagent, being hydrogen peroxide, those aldehydes would instead be carboxylic acids. So it's important to be careful. Okay, now we just need to convert our starting alkyl halide into this alkene. And we know we can do that through an E2 reaction. We just have to pick our reagents. I encourage you to pay very close attention to the reagents you use, because for something like this, we could draw the double bond in one of 2 places: the blue where we want it to be, or the red where it could end up by accident. All I will tell you to do here is to use an unbulky, unhindered base. So I would use NaOCH3. You could use NaOH, something like that, because that will let you end up with the Zaitsev's more substituted double bond product, as opposed to the Hoffman product that would happen in the case that you use a bulky base. So this is a complete synthesis for this problem. Let me know if you guys came up with any other ways of doing this, but this is how I would do it. Okay, let's do one more. You know the drill. Try it on your own first, and we will come back and do it together. Per usual, we can ask ourselves what stayed the same and what changed. Initially, in this case, I'm just looking at the functional groups. In the starting material, we have an alcohol, and when you have an oxygen bonded to 2 alkyl groups, that is called an ether. I then immediately compare the R groups of each. Because the alkyl group of the alcohol and at least one, this just happens to be a symmetrical ether, but at least one of the alkyl groups of the ether are identical, we can assume that this and this are the same. So now if we were to break these up, this would equal plus hydrogen ion. And again, with that portion being equivalent, you would have this as the intermediate. So now in the step converting the intermediate to the product, we have to consider how we can add 2 more carbons to the intermediate. I'd like to point out that this oxygen with a negative charge is a good nucleophile. And when you start thinking about nucleophiles, hopefully you think about substitution reactions, specifically SN2. The other part of our SN2 reaction is an alkyl halide, and we need to pick our alkyl halide to match this other arm of the ether. So I would see carbon 1 and 2, and then I would draw in the alkyl or the halide. So I'll just write bromine. Now all that needs to be done is to deprotonate the alcohol, and the only necessity for that is to use a stronger base than the alcohol itself. Oftentimes, and this time, you will see sodium hydride, not only because it's a very strong base, but because the product would be the deprotonated alcohol, so the base that we would use for our nucleophile, but also hydrogen gas. And because it's gas, it will leave the solution on its own, so this would be an irreversible step, which would make our synthesis more efficient. But with that being said, this is a complete synthesis for this reaction.